Welcome to The Explainer. If you've spent any time at all poking around modern AI, you've definitely heard folks call neural networks black boxes. But today, we're going to completely shatter that myth. Because the truth is, we aren't looking at black boxes. We're looking at highly structured, meticulously designed architectural blueprints. Literally, just like a skyscraper relies on its steel framework to stand up, an AI model's capabilities are entirely defined by its underlying architecture. So let's just dive right in and decode how these structures are actually built from the ground up.
So, what would you say is the absolute most consequential design decision you can make in any deep learning project? It is so tempting to just say, oh, it's the data set. And yeah, for sure, data is absolutely crucial. But the real answer, it's choosing the right architecture. As our source material points out, the blueprint you choose dictates literally everything, from the model's capacity to represent complex ideas, to how it actually trains, to what it's ultimately going to cost you in compute. It fundamentally decides how well your model handles different kinds of data, whether we're talking about images, text, or audio. Here's our quick roadmap for today. We'll hit the blueprint concept, the dimensions of design, check out the math engine, look at the plumbing and training, and then finish up with CNNs versus transformers.
All right, part 1. The blueprint concept, structuring intelligence.
As the quote here says, artificial intelligence architectures define the structural blueprint by which a model receives, processes, and outputs information. Look, over the last decade or so, we've evolved from these super simple perceptrons all the way to massive billion-parameter transformer networks. But the core concept? That hasn't changed a bit. You're building a pathway for information. The model needs a foundation to dictate how data flows. If you're building an AI, you are quite literally an architect. And you've got this incredible palette of options to choose from, depending on whether you need to process spatial images or handle super long sequences of text. Moving right along to Section 2, Dimensions of Design, the trade-offs.
Let's look at the literal physics of AI design here. Think of these dimensions just like you're constructing a physical building. Depth, which is the number of layers, is like adding floors to your skyscraper. It controls the hierarchical feature abstraction, letting the model learn much more complex, nuanced concepts. But what's the trade-off? Expressivity versus vanishing gradients. If you build it too tall, the learning signal just gets lost before it ever reaches the ground floor. Then you have width, which is basically your square footage per floor. That gives you representational breadth, but boy, does it cost you heavy compute and memory. You've also got connectivity patterns dictating how the information flows, balancing generalization against overfitting. The big takeaway here? Every single dimension you push in one direction pulls back in another. It is a constant balancing act.
Okay, Section 3. The math engine, feed-forward networks.
Now please don't let the math on screen scare you off. This isn't just a dry equation, it's a super elegant dynamic recipe. What you're looking at is the multi-layer perceptron, or MLP. Information here propagates strictly forward. In the forward pass for any given hidden layer, let's just call it layer L, the network takes the output from the previous layer, multiplies it by a set of learned weights W, adds a bias B, and then wraps the whole shebang in an activation function. It starts right at the input layer with raw feature vectors and mathematically transforms them step by step until out pops your prediction.
Let's actually break those variables down for a second. So W and B, the weights and biases, those are the actual parameters the model is learning during backpropagation to minimize its errors. They're applying linear transformations. But honestly, the real MVP here is the activation function. Things like ReLU or JeLU. They introduce nonlinearity, and this is absolutely crucial. Without that nonlinear activation, I don't care how many layers you stack, your whole beautiful network would just collapse into one single flat linear equation. But with it, a sufficiently wide hidden layer achieves what we call universal approximation, meaning it can mathematically approximate pretty much any continuous function out there.
Up next, Section 4, Plumbing and Training, Stabilizing the Flow. Take a look at the standard hidden layers on the left there. Like we were just talking about, if you stack way too many of these sequentially, you run right into the vanishing gradient problem. The mathematical learning signal just gets too weak as it travels backward through all those layers during training. But on the right, that's our architectural plumbing. Modern networks use skip or residual connections. Think of these like pressure relief valves. They provide these really handy shortcut paths for the gradient to flow smoothly by just completely bypassing certain layers. Combine that trick with batch normalization, which stabilizes the whole training process and gets you to convergence faster. And suddenly, there's no problem building those massive 152-layer architectures without the model totally collapsing on you.
Which brings us to Section 5, CNNs versus transformers, the clash of biases.
Let's look at the reigning champion of computer vision for a second, the Convolutional Neural Network, or CNN. Checking out this timeline, it's pretty wild. Back in 1998, LeNet-5 pioneered digit recognition with just 60,000 parameters. Fast forward to 2012, AlexNet completely explodes onto the scene, leveraging GPUs and ReLU activations with 60 million parameters. Then in 2015, ResNet drops, introducing those brilliant skip connections we just talked about, which allowed for insane depth efficiently. The scaling here is just staggering, but it's all built on one very specific, very powerful structural assumption. And that assumption? It's called an inductive bias. Let's actually pause on this because it is foundational to everything we're talking about today. An inductive bias is basically a built-in assumption that a model makes about the structure of its own data. CNNs have a massive spatial inductive bias. They use these learnable filters that literally slide across an image, so they just assume that a pattern, like say an edge or a curve, is relevant no matter where it happens to pop up in the image. That's what we call translation invariance. They also naturally assume that pixels close to each other are related. That's locality.
So, looking at the comparison, on the left, because CNNs have those rigid spatial biases built right in, they are insanely efficient and hyper-competitive, especially when you're working with limited data. The architecture itself is doing so much of the heavy lifting. But over on the right, we've got vision transformers, or the ITs. Transformers have way less built-in spatial bias. They just don't assume as much about the structure of the image. Because of that, they are incredibly data-hungry. But, and this is a massive but, post-2020, when we started training them on truly gargantuan datasets, vision transformers started challenging and even beating the CNNs. Why? Because without those rigid built-in biases, they had the flexibility to learn completely new patterns that the CNNs might have just glossed over.
So what is the fundamental takeaway here? Honestly, it's that no single architecture rules them all, period. Building effective AI systems is all about mastering the balance of inductive biases, strengths, and mathematical limitations. If you've got a really limited visual dataset, the spatial biases of a CNN are going to be your absolute best friend. But if you have practically infinite data and massive compute power, the sheer flexibility of a wide, deep transformer might just take the crown. It all comes down to perfectly aligning your blueprint to the specific problem you're trying to solve.
We've covered a lot of ground today, right from the multi-layer mathematical engines and the clever plumbing of skip connections, all the way to the clash of inductive biases between CNNs and transformers. The next time you look at a model, I guarantee you won't just see a black box. You're going to see the scaffolding, the mathematical flow, and all the deliberate, agonizing trade-offs those architects had to make. Which leaves us with one final thought to chew on. As you look at your own data sets and the unique problems you want to solve, which architectural trade-offs are going to define your next AI blueprint? Thanks so much for joining me on this explainer. Keep building, and I'll see you next time.